two lines, well, there just aren't two lines, there's only one, so FPP2 is trivially satisfied. And so this we don't like, and so we rule it out. This we don't like. What I'm doing right now is I'm going through a bunch of degenerate models showing how they satisfy FPP1 and FPP2, but they don't satisfy FPP3, thus explaining the need for FPP3 and the power of FPP3. What else? I guess the analog of this one would be, or the analog of this one would be if you had two lines and they intersected at just one point. That would satisfy FPP2, and it would satisfy FPP1 trivially if there's only one point in your entire model. So that we want out. What's the analog of this one? The analog of this one would be if there was one point only, but a lot of lines through it. This would satisfy FPP2, but it would not, and it would also satisfy FPP1 trivially. Okay, the final model is the model in which there's a line with, say, 2 points on it, and there's a line like this. It's the triangle model. Here there are, through every 2 points there's a line, through every 2 lines there's a point, but that's all there is. So if you had precisely 3 points and precisely 3 lines, meaning in a triangle formation, this would satisfy FPP1 and FPP2, but we just don't like this model because it's very boring and nothing really exciting happens here. So this is the last model which we're going to consider degenerate. And FPP3 to the rescue. FPP3 says, yo, your model has got to be more interesting than any of these. And so we can ignore these degenerate models, which are going to cause us a lot of headache with having to constantly talk about special cases. And we can just talk about models that are kind of interesting. And for our model to be interesting enough to talk about and to be an actual finite projective plane, there have to be these 4 points, at least 4 points. And not just any 4 points, because this model has 4 points, but 4 points that are not all on a line. Okay, and anything that satisfies these is a finite projective plane. I rambled on about duality, about how points and lines now have the same relationships to each other. Well, FPP3 has an analog, or a dual theorem called FPP3 prime. And FPP3 prime says that there are 4 lines, no 3 of which go through a common point, or no 3 of which concur. And the very first thing that's going to happen in the very next video that you're going to watch, if you're watching this in order, is a proof, a very sort of tedious, slow, careful proof of FPP3 prime from these 3 axioms. In fact, I think I did the proof on the board, but wasn't recording, and then went back after class to finish the proof. So you will now start watching, if you're watching this in order, the very next thing will be me doing this proof, but almost the entire proof is already written on the board, and I'm just explaining the last couple steps. Okay. Good. Bye.